Okay, so let's go through a handful of these problems. Let's just read through it. It says Tina can run 100 meters in 12.5 seconds. How fast is this in miles per hour? So this is going to be a conversion problem. So we're going to start with our units, 100 meters in 12.5 seconds. So we are going to write our typical conversion. 100 meters is equivalent to 12.5 seconds. So now what we need to do is convert this to miles per hour. So again, when you see the slash, it means divide, or if it was a word per, it means divide. And I'll try to make my writing a little better here. So we need to convert our numerator, the meters, to miles, and seconds to hours. Well, let's convert seconds to hours first because that's the easier one. So we'll draw our first conversion factor. We're trying to convert seconds, so we're going to put that in the denominator. And let me get rid of this just to not confuse things. There we go. Alright, so, and then we want to convert from seconds to hours. Now, if you know the conversion from seconds to hours, it's 3600, but let's just say you know that there are 60 seconds in 1 minute. That way, seconds cancel. So now we have meters per minute, but we need per hour. So we're going to put minutes up here so it cancels, and hours. And there are 60 minutes in 1 hour. Minutes cancel. So if we stopped right now, we would have meters per hour. Well, we don't want meters, we want miles. So we need to convert meters. So we're going to put that in the denominator. Now I don't know what the conversion from meters to miles is, but I do know that there is 100 centimeters in 1 meter. The reason I'm doing this is because I know how many centimeters are in an inch, and then I can go from feet to miles. So meters cancels. We have centimeters, so I'm going to move down here. I need centimeters in the denominator. And again, I know that there are 2.54 centimeters in 1 inch. So centimeters cancel. Now I have inches. So we just keep doing what we do. I want to get rid of inches, so I can go to feet. There's 12 inches in a foot. Inches cancel. And then I can go feet to miles. 1 mile is 5,280 feet. So what you're going to see is everything cancels except miles per hour. When I go through and do the math, remember everything in the denominator is times. So 100 divided by 12.5 times 60 times 60 times 100 divided by 2.54 divided by 12 divided by 5,280 is going to give me 17.9 miles per hour. And that's actually pretty fast running. Not super fast, but pretty fast. Alright, so let's move on to the next one. Let me do some switching here. We need to clear that, so let me see if I remember how to do this. Alright, let's go back to our pen. Alright, this one says Amanda performs 3 trials on a lab to determine the boiling point of water. She finds the boiling point to be these 3 measurements. Now we know the boiling point is supposed to be 100 degrees Celsius. That should be common knowledge at this point. So this is a question asking about the terms accurate and precise. Remember, accurate means you're getting the correct data. Precise means that your data points are all close to one another. So as you can see, these data points are pretty close to one another, so we're going to say they're precise, but they are certainly not accurate. That 130 is pretty far away from 100. If we had gotten like 102, 101, and say 99, those would be precise because they're close to one another, but then they would also be accurate because they're close enough to the right answer. Alright, so then we're going to calculate percent error, and if you remember, percent error is going to be your theoretical minus experimental, or the right value, so it's 100. In other words, that's what the value should be. we would take the average of our three values there, and if you average those, you're going to get 130. So that would be our experimental value over our theoretical. We're going to times that by 100, and it's going to come out to be 30%. So that's pretty bad percent error for measuring the boiling point of water. Clearly, you need a better thermometer. All right, let's move on. I'm gonna click to the next page. Let's clear. We're gonna get rid of that, and let me get my pen back. Okay, the density of iron is 7.874 grams per cubic centimeter. And I want to know how many kilograms there are in an iron slab with these dimensions. So if you remember, volume is equal to length times width times height. So we have our three volumes, length times width times height. Now here's where the whole point of this question is going to come in. You can see we have the unit cubic centimeters, and our length units are given in meters, meters, and centimeters. So what we're going to do is convert that one to centimeters. And remember, from your King Henry died, unfortunately, drinking chocolate milk, to get from centi to the base unit is 2 places. So we're going to move our decimal over 2 places. Move the decimal over 2 places for the next one. 150 centimeters, and then 25 centimeters. So this is going to give us, when we're done, centimeters times centimeters times centimeters is centimeters cubed. So when you do that math, you should get a rather large number of 168,750 cubic centimeters. So that's 1,687,500 cubic centimeters. Alright, so what we're going to do is we have a compound unit and a single unit, so we always start with the single unit. 1,000 or 1,687,500 cubic centimeters, and we want to get rid of cubic centimeters, so we're going to put 7.874 grams per cubic centimeter in the denominator, so those will cancel. Now we have grams, and we want to get kilograms, so we will go grams to kilograms, and using our King Henry's help, we know there are 1,000 grams in 1 kilogram. So grams cancel, and we have kilograms. So again, we have a basic dimensional analysis problem. When you do the math there, you should get 13,287 kilograms. And that's a lot of weight, but you're also talking about a slab of iron. Okay, let's move on. Let me move to the next slide. Let's clear that and get a pen. Okay. So now we have another precision problem. We have 1 hour measured by an accurate chronometer, whatever. So we have 1.000 hours. In other words, that's very precise. It's at 1 hour exactly. And your wristwatch is measuring 1 hour and 12 seconds. And we're trying to figure out what the percent error is. Let's not worry about the sig fig stuff right now. Alright, the mistake that people make is they'll go 1.12 as our measured value, but what we need to do is convert 1 hour 12 seconds to just hours. So we're going to convert seconds, 60 seconds, to hours. Seconds cancel, and we're going to get 0.2, I believe. Yeah, so that's 0.2 hours. So 1 hour 12 seconds is actually 1.2 hours. So then to solve for percent error, we're going to have our theoretical value minus our measured value over our theoretical value times 100, and that is going to give us a 20% error. And always look at your numbers and see if they make sense. 20% of 60, when you think about it, we're off by 12 seconds, so that should make sense. Okay, let's move on to the next one to try to save a little bit of time here. Let me get my cursor. We will move to the next slide. Let me clear out the writing here and get a pencil. Okay. This problem's a little bit more involved, and it's going to actually measure a few things. We have a bathtub with 1.15 square meters with an average depth of 0.4 meters. We're looking for quantity of heat, so anytime we talk about heat, we're going to use our formula MC delta T is equal to our heat. We want to raise the temperature of the water 2 degrees Celsius, so our delta T value is 2. Water has a C value of 4.18. So what we need is M, and then we can calculate Q. Well, we know water has a density of 1 gram per milliliter, and we know that 1 milliliter is equal to 1 cubic centimeter. So what we want to do is figure out how many cubic centimeters this is. Now you could convert these from square meters to square centimeters, or you can multiply these two together, and when you do that, you would get 0.46 meters squared times meters is meters cubed. Now what we want to do is convert meters cubed to centimeters cubed. Meters, centimeters. There's 100 centimeters in 1 meter, but remember, we need those cubed. So 100 cubed is going to be 1 times 10 to the 6th centimeters cubed. 1 meter cubed is 1 meter cubed. So when we do that math, again, we'll get a fairly large number, 460,000 cubic centimeters, which is equal to milliliters. So to figure out our mass of water, remember 1 milliliter of water equals 1 gram, so that's going to be the equivalent of 460,000 grams. We're going to put that value in for M and then do the multiplication here, and you're actually going to wind up with 3,845.6 joules. Alright, I went through these a little fast, so use this as a guide, and then as usual in class, ask questions if you have them.